Alright, I'm just continuing where I left off. The last video was on Enums, and this is going over the match control flow operator. The Enums section left us with a cliffhanger of how to use match, and I just wanted to get to it immediately. Alright, so the match control flow operator. Rust has an extremely powerful control flow operator called match that allows you to compare a value against a series of patterns and then execute code based on which pattern matches. Patterns can be made up of literal values, variable names, wildcards, and many other things. Chapter 18 covers all the different kinds of patterns and what they do. The power of match comes from the expressiveness of the patterns and the fact that the compiler confirms that all possible cases are handled. Okay. Think of a match expression being like a coin sorting machine. Coins slide down the track with variously sized holes along it, and each coin falls through the first hole it encounters that it fits into. In the same way, values go through each pattern in a match, and at the first pattern the value fits, the value falls into that associated code block to be used during execution. Because we just mentioned coins, let's use them as an example using match. We can write a function that can take an unknown United States coin and in a similar way as the counting machine, determine which coin it is and return a value in cents as shown in listing 6-3. Okay, so let's empty this main function. Let's create our enum. We'll have an enum called coin, and it's going to have variant of penny, nickel, dime, quarter, and then we're also going to have a function value in cents. And it's going to take a coin, which is our enum type, and then we're going to return U32, which is a unsigned integer, because coins can only be positive, and return that. And then we're doing the match expression. This is what we want to learn. Match coin. And like they were saying in the description, we have each type here, or each variant of our coin, because the compiler is going to make sure that we match to all different combinations. Seemingly, when writing the matches, if we miss a combination or possible combination that it can output or reach, the compiler will yell at us. So coin, and if it's a penny, return 1, coin, nickel, return 5, coin, dime, 10, coin, quarter, return 25. And I think we could test this out. Do a print. So I can say, I can create a value of coin and let that be, let's start with a penny. Coin, penny, and it doesn't take in anything. So that should be fine. And then in here, we should be able to print out the value of it by using the function value and then passing our coin. Let's see if that works. Oop. Close this. Cargo run. It said it could not compile. Coin penny. I may be instantiating this incorrectly, or it may not be an expression. Any other issues? Try that again. Nope, nope. I was just defining it wrong, instantiating it incorrectly. So when we take out the parentheses, we have our coin, and then we print it out 1. All right. So let's try a nickel. 5, dime, 10, and last but not least, well, the greatest actually, quarter. Cool. Let's break down the match in the value and cents function. First, we list the match keyword followed by an expression, which in this case is the value coin. This seems very similar to an expression used with if, but there is a big difference. With if, the expression needs to return a Boolean value, but here it can be any type. The type of coin in this example is the coin enum that we defined on line 1. So you have match, and we're matching to coin, and this type of coin is this enum. Next are the match arms. An arm has 2 parts, a pattern and some code. The first arm here has a pattern that is the value coin penny. So right here, they call this the arm, and then this arrow operator that separates the pattern and the code to run. So this is the code to run. The code in this case is just the value 1. Each arm is separate from the next with a comma. Okay, so what they're saying here is that this is an arm, this is the code that's going to run, this operator points to the code that's going to run, and the separation between this arm or this block and this block is the comma placed afterwards. So essentially, if we really wanted to, we can probably put a lot more stuff here, put a comma after that, and then that would be an entire arm, and then we move on to the next one. When the match expression executes, it compares the resulting value against the pattern of each arm in order. If a pattern matches the value, the code associated with that pattern is executed. If the pattern doesn't match the value, execution continues to the next arm, much as in a coin sorting machine. We can have as many arms as we need. Listing 6-3, we have 4 arms. So what they're saying is here, they're telling us about the order of which the match happens. The coin is going to come in, and then we're going to check this one in order. We're going to go for the first, see if this one matches. If it does, return. If it doesn't, move on to the next one. If this one matches, return that. If it doesn't, move on to the next one. So the first time the coin comes in and finds the match is where we do the execution of code. This seemingly implies that if there is a coin that comes in, or a value that comes into a match, a generic match, and there are 2 different arms that are valid for that piece of information, that data that is matching against, the first one in order going down is the one that's going to be ran. And then the second possible match is never going to execute. The code associated with each arm is an expression, and the resulting value of the expression in the matching arm is the value that gets returned for the entire match expression. Curly brackets typically aren't used if the match arm code is short, as in this case that we have, where each arm is just one value. If you want to run multiple lines of code in a match arm, you can use curly brackets. For example, the following code will print lucky penny every time the method was called with a coin penny, but would still return the last value in the block. So yeah, let's write that out just so we can see what it looks like here. So let's put this in a code block. Code blocks are expressions. And if we wanted to, we can do a print line here, kind of like debugging, saying, oh, penny was matched. Lucky penny. And then if we change our example to penny here and run it, we should see that. Lucky penny, 1, and The reason why this still returns a 1 is because that is the last thing in the expression. That's good to know. Patterns that bind to values. Okay. Another useful feature of match arms is that they can bind to the parts of the values that match the pattern. This is how we can extract values out of enum variants. As an example, let's change one of our enum variants to hold data inside it. From 1999 through 2008, the United States minted quarters with a different design for each of the 50 states on one side. No other coin got state designs, so only quarters have this extra value. We can add this information to our enum by changing the quarter variant to include a US state value stored inside it, which we've done in listing 6.4. Okay, I guess I can write some of that out. So they have here US state, and they also define that enum type, enum US state, and they have a bunch of states. Well, they don't have a bunch of states here. They have like 1 or 2. I'm gonna say New York, and I'm gonna say New Jersey, and I'm gonna ignore the rest. And then, so that it can be printed out, they have a debug statement. Derive. This is the first time I'm actually writing this out. Last time I just copied and pasted. And they have the comment, so we can inspect the state in a minute. Alright, so they have that there so they can print out what the enum is. And then we have the quarter with US state. So, so I guess the match now has to change. Yep, it does, because I see this underscore red, so that's an error. Let's imagine that a friend of ours is trying to collect all 50 state quarters. While we sort our loose chains by coin type, we'll also call out the name of the state associated with each quarter, so if it's one our friend doesn't have, they can add it to their collection. In the match expression for this code, we add a variable called state to the pattern that matches values of the variant, code quarter. When a coin quarter matches, the state variable will bind to the value of the quarter state. Then we can use state in the code for the arm, like so. So what they're saying here is that we can give this a name, call it state, and the type is now printed out there. And then we can make this a code block if you wanted to. Yeah, they did. 25 is going to be returned, but because our friend may want this quarter, we can print out the name of the state. And state quarter from, and they're doing the debug signature. And they put an exclamation point. State. Give me a semicolon, or semicolon. And then let's try our quarter. And then we have to pass in a state. US state. And pass in New York. Hopefully that works. A state quarter from NY. Alright, enough partying. Let's go. Alright, so that worked. Yeah, this is just explaining what we just did here. So now back to the point that they started off with from last section. Matching with option T. Finally. In the previous section, we wanted to get the inner T value out of the sum case when using option T. We can also handle option T using match, as we did with the coin enum. Instead of comparing coins, we'll compare the variance of option, but the way the match expression works remains the same. So what they're saying is that we're teaching this match because we can use match the way we've been using with coins with option T. And option T only has two variants, sum and none. So let's say we want to write a function that takes an option I32, and if there's a value inside, adds 1 to that value. If there isn't a value inside, the function should return the none value and not attempt to perform any operations. So they have a +1. My editor's getting a little crowded. I'm gonna leave the, I'll just erase the coin stuff. I don't think I need it. But I do need to write a function called +1. So we have a function called +1, which takes in x as an option I32, and it returns an option I32. That seems kind of useless, but okay. I32. And then we have our code block, and we have a match. We match x. And if it is a none, we return none. Oh, I see what they're doing this for. This is an example of how match works. Like how, not match, option. Option probably under the hood uses a match to make sure, or to define whether it's going to be a none or a sum. And that's what we're doing here. We're kind of replicating it. Because sum is going to take a value I. It's going to have an I associated with it, which is I32 now. And here's where we have access to the value. So sum I +1. Okay. And then here we can start messing around with it. Let 5 equal, wow, I misspelled plus. Let 5 equal sum 5, right? Let 6 equal +1 and pass in our 5. And then let none equal our +1 and pass in none. So here they're demonstrating how we can take in a value associated with sum for our option T. Option has variance, none, and sum. And sum is always going to have a value associated with it. And then act on that value. And if we want, return another option. Or I guess anything we wanted at this point in time. It's just an expression. Okay. And let's just run that to make sure it compiles. Oh, that's not a semicolon, that is a comma. It compiled, but we didn't use anything, but it compiled. All right. Let's examine the first execution of +1 in more detail. When we call +1 5, the variable x in the body of +1 will have the value of sum 5. When then compared against each match arm, none equals none, the sum 5 value does not match the pattern none. So we can continue to the next arm. Sum, oh, that matches. Does sum 5 match sum I? Why, yes, it does. We have the same variant. The I binds to the value contained in sum, so I takes the value 5. The code in the match arm is then executed, so we add 1 to the value I and create a new sum. Yeah, we create a new sum value with our total 6. Yeah, that's a new sum. Now let's consider the second call to +1 in listing sys.5, where x is none. We then enter the match and compare to the first arm. We have none equals none. that matches, there's no value to add to, so the program stops and returns the none value on the right side of the arrow operator. Because the first arm matched, no other arms are compared. Combining match and enums is useful in many situations. You'll see this pattern a lot in Rust code. Match against an enum, bind a variable to the data inside, and then execute code based on it. It's a bit tricky at first, but once you get used to it, you wish you had it in all languages. It's consistently a user favorite. That makes sense. My nose. Matches are exhaustive. There's one other aspect of match we need to discuss. Consider this version of our +1 function that has a bug and won't compile. So in this version of +1, they took out the first match. And as you see, this went red and says it must be exhaustive. And if we were to run this, we didn't handle the none case. So this code would cause a bug. Luckily, it's a bug Rust knows how to catch. If we try to compile this code, we'll get non-exhaustive patterns, none, not covered. And let's just verify that, because I know last time we got a different error than the one they were saying we would get. No, same here. Cool. Rust knows that we didn't cover every possible case and even knows which pattern we forgot. Matches in Rust are exhaustive. We must exhaust every last possibility in order for the code to be valid, especially in the case of option T, when Rust prevents us from forgetting to explicitly handle the none case. It protects us from assuming that we have a value when we might have null, thus making the billion-dollar mistake discussed earlier. So yeah, this is saying that Rust made the decision to sort of protect us from the billion-dollar mistake, which is assuming that we have a value when we don't have a valid value, the none value that was discussed earlier in the snippet. The underscore placeholder. Rust also has a pattern we can use when we don't want to list all possible values. For example, a U8 unsigned 8-bit integer can have valid values from 0 to 225. If we only care about values 1, 3, 5, and 7, we don't want to have to list out 0, 2, 4, 5, 6, 7, 8, 9, all the way up to 255. Fortunately, we don't have to. We can use the special pattern underscore instead. So what they're saying here is there are some times where the exhaustive list can be much more than you really want to write out. And if you only care about some of those values, in this case 1, 3, 5, and 7, you can use this property to have all the other possible matches go there, and that counts as exhaustive because they will just match to this place. The underscore pattern will match any value. By putting it after our other arms, the underscore will match all the possible cases that aren't specified before it. The parenthesis thing is just a unit value, so nothing will happen in the case of when the underscore is matched. As a result, we can say that we want to do nothing for all the possible values that we don't list before the underscore placeholder. However, the match expression can be a bit wordy in a situation in which we care about only one of the cases. For this situation, Rust provides if let. And I'm guessing the next section is going over if let. Let's just check. Yeah, it is. Cool. I'll probably get to that video sometime soon. Well, in terms of this video, I hope you enjoyed it. Hope it was useful. Outside of that, peace.